In many companies today, people literally are drowning in a sea of information. Computers can generate information faster than anyone can keep up with it. So the search is on for a machine solution that will help people deal with the volume of data the computers now provide. There's been a dream in science fiction, as long as there's been science fiction, of machines or robots that could act just like human beings. In artificial intelligence work today, computer scientists are building systems that have the ability to process visual information, that can process natural languages, the languages we talk in, and in a related line of work, they're building systems that they call expert systems, which are systems that mimic the behavior of human experts. Here at AT&T Bell Laboratories and at many other centers, people are working on these expert systems, systems that can follow a complex line of reasoning in a complex and perhaps not very well understood domain to arrive at an interpretation that is similar to the way that an expert would think about a body of data. These systems have been used for medical diagnosis and chemical analysis and in telephone companies. Building this new type of system presents some challenges to the computer scientist. Most conventional programs have been written to solve very well-defined problems, the sorts of problems that can be reduced to a conventional algorithm. Today, solutions are being sought to problems that rest heavily on an expert's experience and expertise, problems where the solutions are not well defined. These are problems where it would be extremely difficult to develop a conventional algorithm, if that were possible at all. Instead, a new technique of program development called knowledge engineering has been brought to play here. Knowledge engineering seeks to model the actual methods that an expert uses to solve a problem and capture them in a computer program. Now, an expert has several things that they would use in working through an amount of data like this. They have understanding of how to analyze the data, they have notions of when to apply that understanding, and also, and very critically for dealing with a large body of data, the expert has shortcuts, methods they use to quickly work through problems rather than working through them step by step by step. A large part of knowledge engineering is identifying those sorts of shortcuts so they can be used in a computer program.
Is there any hot shot favourite that you'd say? I mean, you've seen that it's perhaps lightning damage, which is...
Yes, there's two or three things to it.
In knowledge engineering, our job is to identify a problem area, find human experts in that domain, and draw, or in some cases, tease out their expertise. This is an iterative process where we start with a series of informal interviews. I think it's probably going to be sheath breaks, but you're telling me the problem is in the splice. What is it in the data here that lead you to think that that's a splicing problem?
Well, since the most recent customer problems were splicing.
Next, we draw up a set of rules based on those interviews, and then we review and revise the solutions those rules generate, working with the experts. One of the most powerful techniques that experts use is called heuristics. Heuristics are rules of thumb that provide quick solutions to complex problems. A heuristic includes both a solution or a partial solution and also some notions of when the heuristic ought to be applied. The difficult thing about programming with heuristics for the person doing knowledge engineering is that heuristics tend to be things that an expert knows as a matter of course, but has a difficult time verbalizing or describing as the very things that their expertise relies on. A good example of this is a musician playing improvisatory music, playing variations on a theme. Now, there are techniques that you use to vary a theme, but a musician doesn't sit there saying, okay, now I'm going to use technique 1, then I'll use technique 3, then technique 5 will sound terrific here. The musician has to sit there and actually play the music. Now, you could imagine writing a program that knew those techniques and could call them in, technique 1, technique 3, technique 5, and write or play music on a synthesizer, one supposes. But a musician has to do this in real time. And in general, the musicians will say they just do it. They can't really verbalize how they know what technique to use. The techniques just seem to fit together and come out. The musician would have a hard time verbalizing this intuitive knowledge, especially when they're right in the middle of a performance. Now, debugging computer programs is another example.
What's this line doing?
Just exactly that. It sends the select method to the window with menu.
I see. Oh, then what the problem must be is that this really ought to be an after method rather than a before method. Oh, that'll... Good. Much of what I know about finding computer bugs is impossible to articulate. Often I'll just look at a program that's having some kind of problem and just know what the cause of the problem is and just know how to fix it. I can't say how I've done it, and I don't know how it came to mind. I can't put it into words at all. It's utterly inaccessible to my consciousness. It just happens.
So heuristics are an expert's shortcuts, even if the expert can't verbalize what those heuristics are exactly. Now, other activities that rely on strategy and hand-eye coordination, such as video games, also use a heuristic-like process. Any Pac-Man enthusiast who scores in the hundreds of thousands draws upon private knowledge acquired from many hours of practice. Even though expert players may not be consciously aware of the process, they are continually acquiring data, analyzing relationships, searching for connections, and drawing conclusions or inferences about the best play. This information or expertise is embodied in a set of heuristics, which the expert applies to play a faster, higher-scoring game. Often, more than one rule of thumb or heuristic could be applied in a given situation. Part of the expert's knowledge is knowing which of the heuristics would be the best one in a given situation.
There are good heuristics and there are not so good heuristics. We like our heuristics to be theory or model-based, but we take what we can get. As an example, there is a heuristic that says that fuzzy caterpillars are precursors of bad winters. This has probably evolved through years of observing that very fuzzy caterpillars are precursors to very bad winters. There's no real good theory behind it, but it does seem to have some predictive validity, so we take it. This is one difference between heuristics and algorithms. In algorithms, there's a precise series of steps. You know where you're going and where you've been. In heuristics, you have to uncover when to apply the heuristics and what the heuristic predicts.
So a major component of expertise consists of the expert's problem-solving shortcuts, but that's not the whole picture. Expert knowledge can generally be divided into two parts: knowledge about the problem and knowledge of techniques for applying that knowledge to problem-solving. The knowledge represented in an expert system is also generally divided into two parts. One, usually called the knowledge base, contains domain-specific information as well as rules and heuristics. The other part, often referred to as the control structure or inference engine, contains the mechanisms for applying that knowledge base to solve problems. It's a pretty major task to acquire all the knowledge that's needed for an expert system. Experts don't express their knowledge in the way that you'd want to put it in the computer program. Generally, what we try to do is take the complex information the expert provides and express it in a very simple but large set of if-then rules. Rules that are in the form that say, if the expert system knows certain things to be true, then the system can also infer that something else is true. In this way, the system changes its knowledge about a problem and works toward a solution. It takes a large number of these rules to build an expert system. Now, building the system is both an interactive process and it's an iterative process. It iterates because it takes repeated times trying a set of rules, adding new rules, deleting old rules, changing rules, seeing where the system makes mistakes to bring its performance up to the par that you'd expect from an expert or an expert system. It's an interactive process because it's a process just like I've been describing, one where the experts and the knowledge engineer interact with the expert system, look at its behavior, change its behavior, try to understand and improve its behavior. Expert systems are programs that tend to be relatively easy to modify compared to conventional programs. For that reason, they're particularly well suited towards solving ill-defined, complex problems. A good example of this can be drawn from medical diagnosis, where some of the first expert systems were built. At Rutgers University, Sholem Weiss and Casimir Kolakowski developed CASNet, an expert system that is used for the diagnosis and management of glaucoma.
CASNet was a pioneering effort in knowledge-based consultation systems, which later came to be known as expert systems, in that its reasoning was based on a model of the cause and effect that is described in a network, and this network characterizes the disease mechanisms in terms familiar to a physician. One of the key characteristics of expert systems is that they can not only explain and justify their reasoning, but they should also be able to update their reasoning so as to incorporate the latest research results and the latest results from clinical practice. There has been quite a lot of work in this area, and this work depends primarily on the nature of an expert system that is based on rules. If you have rules that are able to be expressed in a very modular fashion, then it is easy to capture the knowledge and expertise of a human expert in such a way as to modify it later on should those rules not work right.
From the CASNet experience, Kulikowski and Weiss later developed a system-building tool called Expert. Expert retains all the diagnostic reasoning mechanisms of CASNet without CASNet's knowledge base about glaucoma, so it's possible to plug in a new knowledge base for a different problem domain. Such off-the-shelf inference engines make the creation of new expert systems faster and less expensive than starting from scratch every time. So, by retaining the reasoning or inference techniques of CASNet, Kulikowski and Weiss turned a medical system into a geological system called ELAS, the Expert Log Analysis System.
We got together with Amoco, a very large oil company, and we discussed with them the possibility of using an expert system approach in a very novel way. We knew that they had a lot of software for the interpretation of well logs, or the signals that allow them to estimate whether there's oil and how much in a well. And what we proposed was that we would be able to build an intelligent expert system to serve not only as an interpreter of the data that came from these oil well logs, but also as a tutor to stand over the shoulder of the person using these programs, this complex software. There have existed for quite a while several sophisticated software tools for analyzing this kind of signal data, but they have lacked an interpretive component. So they could only be used effectively by highly trained well log analysts, geologists, or engineers. In working with Amoco, we wanted to show that an expert system could be built to make this software understood by others besides the specialists, so that we could incorporate within the interpretive component the knowledge and expertise of the very best log analysts. We have also developed an interactive and easy-to-use interface, including a type of spreadsheet and sorts of graphics displays which allows the user to control the way in which the data is analyzed and to keep track of how the user solves the problem.
Another interesting industrial application of expert systems is at British Steel's Lackenby works. The expert systems terminal has been installed right on the foundry floor to help plant electricians troubleshoot the automatic level controls for the continuous steel casting process. To repair the automatic level control, an electrician has to work on the casting floor. Obviously, the expert system must be located nearby. A terminal is located in each of the main casting control rooms, just a few steps from where the electricians will be working. Like many expert systems, it asks a series of questions. This is not a fixed series of questions. The answer to each question will affect the system's selection of the next question. During a repair, the electrician may have to check with the system several times. This particular expert system can give advice on some 200 different tests and diagnose about 50 different types of faults. So far, we've been looking at the overall concepts that are used in knowledge-based systems and how those concepts have been applied to solve some real-world problems. Now we're going to look a bit more closely at the inner workings of a knowledge-based system. In order to build a knowledge-based system, the developer has to represent the knowledge. They have to provide the knowledge to the computer so the computer can use it, and also record it in a fashion that the developers can understand it. In order to do this, you need a scheme of knowledge representation. There are several ways to do knowledge representation that are in use today. These include production systems, semantic networks, frames, the use of the predicate calculus. Any of these can be used. The choice of which one is used for a given system depends on the type of knowledge that's going to be represented and the type of problem that knowledge is going to be used to solve.
Two of the most common forms of knowledge representation in AI programs are semantic networks and rule-based systems. So-called semantic networks can be viewed as a kind of graph structure, where the nodes are really the entities that the network's talking about, and the relationships between them are indicated by arcs between the nodes. Rule-based systems are exemplified by production systems, where all the knowledge in the production system is represented as an if-then rule. Both the heuristics that are going to be used to search to solve some problem and the particular facts of that domain. The if-then rules consist of an if part, if some situation is true, and a then part, then do some particular action.
In a typical production system, the knowledge base is made up of two parts. There's the production memory, or PM, which is the set of rules the system uses, and there's the working memory, or WM, which is the set of facts or assertions, things that the system knows to be true about the world. Now the productions are each one of the productions is a single if-then rule. It consists of a left-hand side and a right-hand side. The left-hand side is the if side, the side that consists of a set of statements. If they are true, then the rule is appropriate to be used. The right-hand side is a set of actions. These are things that will be carried out if the rule has been shown to be true. Things that are carried out consist of changing the working memory, changing the value of elements, adding new elements, deleting old elements, changing what the system knows to be true. Now, in the operation of the production system goes through the working memory, looking for which left-hand sides of rules can be matched based on what is known, what's true in the working memory. When a match is found, the rule that has been matched fires. It operates. When it fires, its right-hand side actions are carried out. This changes the state of the working memory, and the whole cycle can be carried out again, finding a rule that's appropriate, or finding that more than one rule is appropriate, in which case there's usually a strategy to resolve the conflict and always pick the next rule to fire. Through going repeatedly through this process of finding a rule to fire, firing the rule, changing the working memory, finding the next rule to fire, the system will progress to a solution. And solving a problem consists of repeatedly going through the state of what the system knows, changing it, and changing it again until a solution is reached.
This can proceed either forward chaining through the space or backward chaining through the space. To clarify these searches, let's look at a graphic example using a semantic network. Take Patrick Henry Winston's popular example of African animals. Here we have a semantic network which contains characteristics for a cheetah, a tiger, a giraffe, and a zebra. Now these animals can have tawny color, dark spots, long legs, black stripes, and they can be mammals, carnivores, and ungulates. Finally, they can have hair, give milk to feed their young, eat meat, have hooves, chew cuds, and so on. So let's say we're trying to solve a problem about what kind of animal it is that we're really seeing, proceeding from some kind of sensory input. One way we can proceed is to go from the sensory input itself forward through our representation of what we know until we reach some kind of conclusion. This is called forward chaining or data-driven search. Let's say our senses tell us that the animal has hair, hooves, and stripes. So we know that this OR is now true. This means that the animal is a mammal. This animal also has hooves. So this activates one side of this AND. The other side of the AND is activated by mammal. We now know that the animal is an ungulate. Since our sensory input has told us that the animal has stripes, we know that this AND is true. And finally, from that, we know that the animal must be a zebra. So this is an example of forward chaining. Again, suppose our senses tell us that the animal out there has hair, it has hooves, and it has stripes. The second way we can find out what we're looking at is what's called hypothesis-driven or backward chaining search. In this kind of search technique, we just guess what kind of animal is out there. Maybe it's a giraffe, or maybe it's a cheetah. We proceed to play a kind of 20 questions with the world. We chain back from our assumptions, from our hypotheses about what's true, and back through the network until we reach facts that are true about the world, or until we simply run out of guesses and we've run out of information that we know to be true. So first we guess cheetah. If it's a cheetah, then this and must be true. For the and to be true, all these facts must also be true. Let's look at them one at a time, starting with mammal. For mammal to be true, this or must be true, and this means that the animal must either have hair or give milk. Well, our animal does have hair. We've searched back and met up with one of the facts we knew to be true. So now we can test another condition of the and, which would be carnivore. For it to be a carnivore, this or must be true. But we run out of facts to prove this, so it's not a carnivore. And this disproves this and, so our guess of cheetah fails. All right, next we could guess tiger. That requires this and to be true, which means all of these facts must also be true. We could test them the same way until that guess fails. We could try the same thing with giraffe and run out of facts to prove that guess, because our search finds that has spots is not true, so it's not a giraffe either. Well, we could guess zebra, which requires that this and must be true. For the and to be true, both sides must be true. Sure enough, we meet up with the fact has stripes, so one side of the and is true. Now this other side of the and has the requirement that the animal be an ungulate. To be an ungulate, this or must be true, so we just have to prove either side. Let's try this one, where we have to prove this and. To prove an and, both sides must be true. We know the animal has hooves. That was one of our given facts. Now the other side of this and is mammal, which requires this or to be true, so we need to prove either side. We try hair, and we meet up with another of the facts we know. So the animal has hair, which is enough to prove this or, which makes it a mammal, proving one side of this and. We know the animal has hooves, proving the other side of the and, so the and is true, and that proves one side of this or, which means we've got an ungulate, proving one side of this and. The animal also has stripes. The other side is true, which proves the and is true, confirming that yes, we do have a zebra. A different representation for the same facts is predicate calculus. This is a system of logic that was originally developed to use formal symbols to express the truths of mathematics, but can also be used to express many statements of everyday English. So, for example, this expression in predicate calculus says that if something has hooves, and if it's a mammal, or if something is a mammal and it chews its cud, then it's an ungulate. Let's begin with the two and clauses. First, let's begin to get rid of the x's, because this is all going to be about showing that something everywhere is an ungulate. We only had one variable, so we can drop it. Let's just draw a box around hooves. This stands for the hooves node in our network. Mammal stands for the mammal node in our network. We'll write and as a kind of conjunct, and we can connect. Since and is really the primary conjunct, let's redraw this, moving hooves down and moving mammal down. Let's leave the parentheses here for a moment. Let's do the same transformation over here. We'll write a mammal node and cud node. So now we have a funny mixed representation with a little fragment of network here joined by predicate calculus, the or, to a piece of network here. But we can just take this or, make it a higher node. Connect it here because after all, this or connects the two phrases to the predicate calculus. So now we have this or network implies something is an ungulate. Well, let's just move the arrow around, make it point up, say. and show that something is an ungulate. We almost have what we want. All we need is one more change. In a semantic network, we assume that there is only one node for any entity. So here we have mammal, and there we have mammal. These really should be the same node, so let's just combine them. So now we have something as an ungulate if either it has hooves and it is a mammal, or it's a mammal and it chews its cud. But now you can see that the predicate calculus is just the same as the semantic network we started with before. The two are equivalent.
So predicate calculus and semantic networks are two ways of representing knowledge in expert systems. Predicate calculus is used more widely and is close to the form that appears in production systems. An example which embodies many of these concepts about rule-based systems is a sort of freestanding expert system called ACE, which was developed by a group I was a part of here at AT&T Bell Laboratories. There are more than 2 million miles of local telephone cable in the United States. These cables connect telephone customers to the switching offices. The cables are subject to deterioration and damage. Lots of things can cause them to break. Rodent bites, bad weather, physical accidents, many things. ACE helps the telephone company find those places where preventive maintenance is needed. Every night, ACE automatically searches a large telephone company database of reported cable problems. It diagnoses potential causes and pinpoints the places where preventive maintenance is needed. ACE provides reports to a cable analyzer each morning. The analyzer uses those reports to schedule repairs and maintenance activities on the cable system. To accomplish these tasks, we built ACE in several layers. All the supporting routines for ACE are implemented in Unix running on a 3B2-300 computer. This includes a scheduler that controls when ACE carries out its activities, a database where ACE stores its results till they're needed, and the software that runs ACE's user interface. The expert system portion of ACE, the actual rules, are implemented in Franz Lisp and in OPS4, which is an expert system writing language that is written in Lisp. It was developed at Carnegie Mellon University. The expert system has two major portions. One is a knowledge base and the other is an inference engine. The knowledge base is where ACE keeps the rules and the domain-specific knowledge that is used to carry out the expert activity. The inference engine controls the operations of that knowledge base. In ACE, we've added a third major part to the expert system. That is access to an external database. ACE gets the data it uses in its analyses from that external database. In most previous expert systems, the data had to be put into the system one case at a time, as the expert system analyzed that case. ACE is able, on a scheduled basis, to go to the external database and get large amounts of data on many cases to analyze. The use of the external database is ACE's single most unique feature. The database enables ACE to run essentially by itself without requiring that people spend time feeding lots of information to the expert system for the expert system to analyze. In this, ACE could be a model for many data processing situations where there is a lot of information available in a database, but the information isn't being used, it isn't summarized or analyzed because the information is hard to analyze, or the job is tedious, or too time-consuming, or experts aren't available. This key feature of ACE, its ability to draw inferences from large collections of existing external data, could have important implications for activities like investment analysis or transportation scheduling and maintenance, in fact, for much of the industrial and commercial infrastructure of modern life. As developers, we looked for tools that could speed up our work. Lisp, an interpreted rather than compiled language, supported fast prototyping and is a very powerful tool for symbolic representation.
The flexibility of Lisp and OPS4 contributed to the ease with which we developed the knowledge representation. At first, we tried to deal with formalisms and try to fit the knowledge to the formalisms, and we had a difficult time doing that. We then settled on OPS4, which gave us a rather wide range of flexibility in developing representation. And after a few months, we had a stable knowledge base. But after that time, we could see where other representations could contribute to the knowledge representation that we developed using OPS4. But we were happy with what we had and went on with it. The interactive nature of Lisp also contributed to the overall success and productivity of our project. It was very easy to change, modify, and test rules, which is very important in developing knowledge-based programs by using the Lisp interpreter.
Expert systems have moved beyond the areas of medicine, chemistry, and engineering. Computer scientists today are writing systems that can themselves write computer programs, or design computer chips, or take on efforts of scientific discovery, or even expert systems that themselves can gather expertise and write their own new expert systems. Here at AT&T, we have more than a dozen expert system and artificial intelligence research and development projects underway. One joint effort with Columbia University has taken on the daunting task of developing a machine that can understand connected speech. There are many joint efforts between universities and industry that are tackling equally formidable tasks. In the next 10 years, billions of dollars will be spent in pursuit of developing a fifth generation of intelligent computer systems. While we may never reach the science fiction dream of an intelligent robot that acts just like a human being, the near-term goals of computer systems that can understand the world, that can see the world, that can converse with people in the world, that can carry out intelligent efforts to solve complex problems is near at hand. And the realization of these goals are a major step in the further development of the industrialized nations.